Okay. Hey everyone. For those of you guys who don't remember me or don't know who I am, my name is Bernard. I'm the founder of this student organization many, many, many years ago. Almost way too long at this point. Um, I just graduated, class of 23, and I'm now working for the Space Force, doing unmanned vehicle and space robotics warfare research. So good to see you guys. I'm glad to see that Ethan, John, and everyone who's been a part of the team for so long is still a part of it, and Caitlin, who's also in the room. Um, I know you guys did very very well this year with the tournament, so I want everyone to give themselves a nice big clap and pat on the back. Did a great job with that. Um, okay, let's go ahead and get directly started. So the objective of this presentation is very simple. My We need to figure out why exactly we are still in plastic cans, right? Why our robots are still at least a couple of years behind. Um, Hang on one second. Just PowerPoint just broke me for a second. Use presenter view. Okay. What? There we go. We need to figure out why everything like what our situation is, why everything is like, how we can be better, and sort of learn a more fundamental approach, right? A lot of you guys have begun designing Battlebots, and that's really good news. A lot of you guys started building your own, that's also great news. But design without a sort of end goal as to what are we doing here is going to prove to be an issue. So my objective here today is to just be like, how do we take our robots and make them go even further beyond? How do we take them and say, here's where we're at now, here's where we're at in the future. Okay. And then the arrow's not working. There we go. Yeah. So that's my intro. So these are the two robots that I were last involved with. These are both Justin's. One of which is on the top. That one is a snail, which survived very, very, very poorly. The other one, which was Justin's own customs I bought, which also survived very poorly. Justin was made the president of the Robotics Club because he sent the most robots to fight. Regardless of success, he's had the most robots actually show up to a competition and fight in a competition out of everyone in the club. And so, from those experiences, he's learned that these robots, they don't survive full combat most of the time, and they also damage complex and expensive electronics. Right? So whenever we break a Malenki, that hurts our budget a lot, especially because we're poorer than some of the orgs. So really, the answer is if we want to build above robots that can survive above sportsman class, either in ant weight or plastic weight or fairy weight, we've got to start thinking about new ideas and concepts long before we send the robots into battle. Long before they're at competition, we need to have a good idea of, let's try this technology before we go. Alright? We need a technology upgrade. And so these are the top 5 ways of improving robots, right? That we should probably be exploring. There's the need for armor upgrades. There's creating more effective weapons. There's understanding how to make sure our electronics survive. We need a better understanding of 3D printing, and we need a better engineering design management. These are the 5 things we've got to worry about. Now, normally, if I was still a team lead at this point, what I would say is, let's talk about this. But having been through a lot of the industry a lot more than you guys, my goal is to sort of go through all of them and what I know and see if any of you guys have any sort of ideas, concerns, if you find any of them interesting, etc., etc. Unlike in other presentations, by the way, interrupt me. Don't like, if anything doesn't make sense, don't like just let it skip on. Ask, because otherwise I have no idea how you guys are gauging, especially because I don't have a camera feed anymore. So just let me know, alright? We'll get to that, but the big thing is that we need to start prototyping well in advance and testing well in advance in ways that we can test before going to competition. Before even building the robot, we can test some of our ideas long before we get there. So it'd be a good thing to try. Alright, so the first thing we should probably look at is upgrading our armor packages. armor was the biggest problem that Justin had and faced during his fights, and every single other team besides ours is using some sort of advanced armor, including high school students. Um, they're working with a bunch of different techniques that either you've seen in competition or you don't really know is a thing yet. And so I'm going to go through the ones that we know how to use, and the ones that or you've kind of seen before, and then the ones that we haven't really tried before, but we know either someone else has tried and it works, or it's possible to do with further funding or experimentation. The first one, and the most easy one that we should probably start looking at, is something called Garolite. Garolite is a compressed fiberglass reinforced composite. It's very, very effective at 150 gram and 1 pound robots. This is root mean squared. We competed against them back very, very early on in our competition cycle. I think this was 2022. And root mean squared is a robot basically built out of tape and Garolite. But because of its unique design out of Garolite, it was basically indestructible. If we had robots that were capable of throwing it across the room, it would still hold very effectively. Hello. It would still hold extremely well. And because of that, that's something we should start looking at. Garolite's also very, very cheap. Right? You can probably find a nice sheet of Garolite for about $10, $15. And you can cut it up using very, very simple tools. So I think you can cut one with a knife, given if enough time, but hacksaws and those kind of things will cut through it very easily. But it's also very, very, very rigid. So if you attempt to snap it, it's not going to snap very easily. Right? Cutting it might be a concern, but if you're just trying to snap it, you're trying to bend it, you're trying to break it the normal way that a Battlebot will break. Very, very cheap trick. Any questions? It doesn't. It splinters. When fully pressured, it splinters. Because of that, it doesn't really break in the same way that PLA does, because PLA, it splinters by layer. Here, it can take a couple of hits before those splinters actually cause a full failure, in the same way that wood kind of is. So you'll have a lot of advantage there, right? Yep. Well, it's because it's fiberglass. All right. The disadvantage of Garolite is it can only be cut into flat panels, and so root mean square is very square. You can't really bend it. You can't really do anything fun to it. You've got to make these sort of very tank-shaped like plates. Questions? Yeah, so we can cut it. John was one of the first team members to go up against root mean squared and lose very effectively. You witnessed it. You were one of, besides Justin, I think you were the only one out of the still team who was there to witness it. Yep. Yeah. Yeah. With Garolite, because of the resin that it's done, it's not as dangerous as other things, like full fiberglass plates or carbon fiber plates, but it is still a good thing to consider. So, cut it outside, wear a mask. So Garolite specifically is very, very, very light. I don't remember the exact density because I don't have that number on hand, and but yeah, and we'll get into that when we talk about better ideas for 3D printing design. But yep. The next avenue is thermoplastic plating, and thermoplastic plating was sort of the same concept as Garolite. We take polycarbonate or acrylic, mostly polycarbonate, and we put them into plates on a system to make it structurally sound. The most common way we can see this is in the Viper kits, because Viper kits are everywhere. Um, but you can do that for a wide variety of options, right? So you can do it. You can cut it yourself with a hacksaw with acrylic and polycarbonate. Polycarbonate you cannot laser cut, um, but you can heat shape. So if you have a mold and you have the polycarbonate, you can heat gun it and it will slowly bend. Acrylic will do the same thing, but acrylic is much weaker when you do that. But acrylic you can laser cut. So if we have a laser cutter, which we used to have, RIP Eastside, you can just cut out the exact shapes out of acrylic, and then your robot is ready. At that point, it's like Lego. So for acrylic, 1/8 for just structural, it's not going to take any load. So if it's just like, hey, I need to sort of hold this place together, but I don't need to actually take any damage. And 1/4 inch for actual structural. So like, hey, this side's going to get hit. Works very, very well for 1 pound. And for most instances, 1/8 is very good for all 150. Now that's kind of a generalization. Again, there's situations where it'll still crack, but that's also a good option. It's also easy to acquire because I know we've got a bunch of it lying around. We good? All right. Hey, TJ. Well done, bro. Why are you not? Are you? What university are you in? Welcome to Houston. We'll be happy to take you. Yeah. Yeah, it snaps. Yeah. Yeah. My remembering on that is that it's slightly weaker than polycarbonate, but in terms of material science, but polycarbonate does snap, so that's something that we have to take into account. All right. Any other questions on that? It's around, I want to say 25 to 30 a plate. 12 by 24, so the same size as our trophy plates. So we've got a bunch left over from when we cut the trophy. Oh, those are acrylic, but you know. They can be cut, you just have to hacksaw it. And very, very slowly. Yeah. Well, you don't need a respirator. It's plastic, so it's not going to... Well, unless you... I enjoy my fair taste of microplastics. Um, wow. Wow, cold room. Okay. But, yeah. Hey, what's up, Tyler? Um, but yeah. Yeah, I just... Yep. We can shape polycarbonate with heat gun. I'll get into that in sort of design, but yeah. Okay. The next option that we can start looking at is something called print surface processing. And print surface processing is fundamentally very, very simple. When you 3D print something, you leave these tiny little gaps in the 3D print between each layer, right? There's a lot of things you do to fix that, but the easiest way is to just coat it in epoxy. If we have a big tub of epoxy somewhere, if we just have enough time to do it, before we put electronics in the bot, we can coat the outside of the bot with a glue, which is mostly epoxy, and it'll increase the strength of it by a decent enough margin that it's worth it. Grant, it's other way around. I think it's easier with 150 grams. So if you have 150 gram and you're still 3D printing it, right? And you're like, hey, it's still out of PLA. I don't really know what I'd like to do. Just paint it over with some glue, and with some epoxy, and it'll hold much stronger on the exterior. Yes, it's not a band material. It's a glue. You can glue it over to whatever. It does work for PLA, but it is really really strong in PET-G. In PET-G, the you can get around 10-15% structural increase. That we use that in unmanned vehicles in aerospace. So that's something that we should try doing, and because epoxy is not that expensive. Well, it's expensive, but like you have enough for a lot of robots. So there's a lot of room we could test that. TJ, I saw you on mute. What do you want to say? Oh, sorry. Really? On exteriors? Like it's not allowed. Ooh. Uh, yeah, yeah. Fair point. Um, it would be. I think it would be best if we're trying to go from 150 ferry weight to just 150 full destructive. We can take the same robot design, and just print surface process it, and it'll be fine. And in full destructive, the rules are lifted, and so it does sort of help out a little. So that's not as good as you think it is, John. Like that seems like a good idea on the surface because it's now a smoother front, and you think the layers melt together, but it also increases the chance that internal stress fractures occur if you don't temper it right. Like if you bake it, then yeah, it'll melt properly. But if you just hot glue it, you'll create patterns of strangeness that just don't work very well. So yeah, next. So depending on how many layers you want to put on this, so for a couple of layers that you would need for like surviving a full fairy combat, I think you can get away with just 2 or 3 layers. So it basically adds like less than 5 grams to a bot. Yeah, so you get a for PET-G you get a lot more structural increase than what you normally have, and you could just yeah, it's paintbrush, mix the two epoxy materials together, paintbrush it, and it'll work. Paintbrush it, let it dry, paintbrush it again, and it looks pretty. All right, it's like painting nails, except I don't paint my fingernails. Next, uh, say again. It That's a very good question because that's what we would do if we were building fighter aircraft. Um, the trouble with that is that when you vacuum chamber PLA or PETG sometimes, it'll increase the chance the layers delaminate. There are many reasons for this. Most of it is with moisture. So if your plastic is very moisture rich, it's like PLA absorbs a lot more moisture than you think it does. When you vacuum chamber it, the PLA will start to do tiny bubble bursts. You won't see them, but it'll cause issues. And so, genuinely, just painting it over is probably a good idea. If you want to resin dip it, that's a lot of epoxy. Like that's a pretty big tub of it. Um, for normal like fairy weights or ants, I don't think it's worth it. Um, but yeah, that's a very good question, and that's how we. Again, when you're talking about bigger aircraft, that is exactly how you do it. So good on you. We good? Awesome. So the last one that we sort of have an idea of how to do, and it's pretty easy to do, is one that many of us have seen before. We call it metal body framing. Um, everyone here has done. Has everyone here done a first robotics competition or a Vex competition? Yeah, most of y'all. Who hasn't? I think Caitlin. Oh, okay, okay. Yeah. So Vex first best. Any of it? Okay. Well, Well, in there are many high school competitions where you're required to build robots, right? Um, and in those, there's usually standardized frame parts where you can just bolt the pieces together and it'll work. Most of the time, it's not very structurally sound because these robots aren't really designed to, like, the frames aren't designed to take massive impact or get thrown across rooms. But on the other hand, it makes it very easy to work with, just directly to metal. And so my favorite design that I've seen that used metal body framing was, if anyone's John, you remember the FRC 2x4? Like the aluminum 2x4? Like, you remember when you were building FRC robots, we had this very regular shaped metal. So yeah, like the, let me Google it for you. Yep. It's 3 your time. I've got to go at 4, but yeah, 4 your time. Yeah. But so someone just filled in and used that as your body, and then filled the inside of it with electronics, and that was their battle button. It was such a uniquely cute design that I was like, that's a great idea. And so if we take this and sort of work with it to say, hey, how do we make sure that it survives? There's a lot more options you can do there to very quickly get to one pound, right? Yeah, you can, and it'll hold in competition most of the time. So you can just put together the robot and say, hey, let's test the idea out. Let's test the strategy out and go from there, right? I'll look because because I saw that robot. I saw that robot. I don't remember if I saw it in person or if I saw it virtual. I saw it in person, but I'll see if I can find a photo of it. Yeah, it's such a cute idea. Um, okay. After this is stuff that we haven't done before, and that'd be very difficult, but it's something that we'd like to try. And if anyone wants to try it, that's a thing we could try. The first one is carbon fiber or actual fiberglass plating. So Garrett Light's relatively easy to work with because you can cut it and score it, and it won't really produce a lot of fibers. With carbon fiber or fiberglass plates, you've got to really think about how much difficult it is to manufacture. Um, Carbon fiber plates are very hard to process. They produce a lot of carbon fibers, and those fibers, when inhaled, are very bad. Um, if when you cut it, you probably have to go get a specialized machine, or find someone who has the right tools to cut it for you. There's very low chance that at the University of Houston you can manufacture that yourself. Back when I was at UH, what we did was we went to Justin doesn't know what's going on. Back when I was working at UH, we went to HTC to manufacture ours. And HTC still has an agreement to some degree. I don't know how much of it's left, but if you reach out to them and say, hey, I want this part manufactured. I'm the robotics club at Houston. Can you help with that? They'll probably say yes in exchange for you sticking an HTC sticker on the side of it. So the other thing is that carbon fiber plating is also, you kind of have the same problem as Garolite, where you have to think about it only as very rigid plates. There's not much bending. The other challenge that is with carbon fiber plating is that if it actually breaks, and so if you design, it won't break unless you design it to break. But if you design it to break, then it's very dangerous to handle. And so if it fractures or fibers off or peels, you'd have to throw away the entire plate. It's very not recommended to try and re-glue that plate back together. Shoot. Yeah. Yes. So carbon fiber is a very strong RF insulator. It's a problem we deal with in aerospace quite a bit because when we build aircraft out of carbon fiber, hey, by the way, none of your drone's communication signals are working. What the hell do we do now? Which, by the way, is one of the reasons why one of the vehicles for the Air Force is having a little bit of trouble, but I'm not going to get into that. We are, like, the easiest way to do it is to design it with multi-material in mind. So with carbon fiber plating, you're not going to design that to just be, like, kind of like the photo. You're not going to design that by itself. You can design it with a frame around it. Leave small section of that frame exposed where your antenna will go, or the Malenki goes. So you could just stick it there, and it'll work. Yeah. Yeah. Because it'll just it's feed forward current, if I remember correctly, because my EC is kind of dying. And that can go really badly. And so heat shrink on all wires would be a requirement for that. Good catch, TJ. So did I. I have a drone in my hand right now that melted down because carbon fiber plating. Fun way. That one melted? Yeah. Ooh. Alright. Well, the nice thing about carbon fiber plating is that we can take a step back. We don't need to go carbon fiber first. So if we start with acrylic or Garolite and say, okay, this Garolite or acrylic is breaking much faster than we want it to, and we want it to be thinner, maybe we can go up. And so don't immediately think carbon fiber cool. Think, okay, this design needs it, and we go from there. Make sense, y'all? Okay. Epoxy coated layering is the next sort of thing. I am working on this as a research paper. It's very hard when you don't have a material science lab, but I'm working on it. The idea is that when you have a 3D print, right? So like this is a 3D printed chest plate. What you do is if you apply epoxy over it, it'll hold a little bit. But if you apply fiberglass plating over it, or carbon fiber, like fiber onto it, and then epoxy that to the plastic, suddenly you go from I have a piece of plastic to I have a carbon fiber thing or a plastic thing, right? And since it's bonded directly to the plastic, it makes it a lot stronger in most aspects. This is something that is very experimental, and I'm still working on to sort of get a good feel for it. But you can design things with significant weight reduction and just putting fiberglass layers over it, and then immediately it will work great. At least from me crashing 2 drones into a wall and going, oh hey, they didn't even break this time. So right now this has mostly been done on cosplay. It has not been done yet on it has been set up to that's not true. Over here you can see this guy on YouTube did one on wood, did one on a regular piece of PLA, and then one on a 3D printed PLA. And found the PLA one was the strongest one out of all the 3 because the little ridges in the fiber, like ridges in the 3D print, allowed the fiberglass and epoxy to hold better to it. And so we may get really a ridiculous strength out of it. I don't know yet, but you could try it. It's very easy. You just take your robot that you 3D printed out of PLA or Petchy, and say, okay, I'm going to layer some put one layer of epoxy on it, or like put the cover it in fiberglass, cut the fiberglass, and put the second layer over it, and it should be much more stronger. So yeah. Any questions on that? Alright. Okay. Yeah, I'm recording this. Yeah. Alright. The next one we can sort of explain is exotic 3D printed materials. John is a huge fan of these. Although I'm a little bit, and so is ASME, but I'm not. 3D printed, exactly, there are many 3D printable materials besides PLA and nylon. This chart is mostly metal fibered, but you can sit down and say, hey, what kind of material should we try besides that, and will it help? The most common one for our robots is TPU. TPU is nice because it doesn't damage the nozzle very. I actually don't think it damages the nozzle much. So you can use it the same way you use PLA, and it's not going to break anything, right? It's also much more flexible, so it's almost like rubber. I think it's actually a latex material. So when you squish it, it'll squish. So if you combine that with something nice like Garolite to provide that extra strength, you can throw your robot across the room, and it'll be fine because the squishing will take most of the impact. And then if it gets hit or stabbed, it'll still hold because the Garolite will take the rest of it. So that's something that Justin experimented with. It didn't go very well because because Justin, but it's something that we can try, right? It's really good. Yeah, it's really good in the 150s. Yeah. Christ Almighty. Yep. Yeah, it's just temperature control that you need to change, and that's it. Well, yeah. 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 Yeah, TPU printing is a little bit slower, and it's a little bit hotter. So the biggest problem with printing TPU is that TPU costs I think usually 2 3 times PLA. Actually, straight up, I think it costs 2 times PLA. And so if you're printing a TPU, fine. You better hope that's fine. The other thing about printing a TPU is that you have to think differently, right? With PLA and with AB and with PETG, you sort of have the expectation of it'll snap before it breaks. With TPU, you have to think about it'll wobble, right? It'll squish, like a plushie, right? And yeah, you can throw your plushie across the room, but if you have a piece of electronics inside that plushie, it's something you ever think about. So that's what went wrong with Justin's robot. This robot was a TPU outer shell and a TPU inner shell, and so when it was thrown against the wall, the electronics would bounce everywhere inside the robot, including the battery, which was not secured down. And so yeah, yeah. So you've got to think about that a lot more, and you can't just secure it down, like by bolting it down. But we'll get into that in a minute, right? Some shoot. TPU it's a 1.75 millimeter filament, so like roughly 2 millimeter filament. That's around I think 70 to $80 is the last one I saw it at. It might have gotten cheaper. It's half of that now. It's half of that now. Motherfucker. Okay, I'd like to point out when I started 3D printing, which was 2015, NinjaFlex was the only one making TPU. So that explains my price expectation. Yeah. It's not bad, actually. So we can probably start getting some TPU filament in and just start testing it, right? Does that make sense? That's something... No, because it's too easy to print. But I'm pretty sure John's got a roll somewhere, and I know Justin's got a roll somewhere. So... No. Oh, I don't know, but you can print it on a normal printer. It's really not that bad. Yeah, so you can print it on an ender. Yeah. Yeah. There's some... Yeah. Yeah. Yeah, you gotta get a dehumidifier, which... Hey, IEEE has one, doesn't it? I wonder why. Um... The nice thing about moving to New Mexico is that I can put TPU with want and abandon. Because it's so dry out here. that I have that it just prints fine. I have no problems with it. But yeah, okay. The last one that we should talk about in terms of material science, and this is solely materials, is billet machining, which is ridiculously expensive but ridiculously strong. How it works is you take a physical cube of something you want, of a material, and you just slowly start cutting into it. You cut the robot shape out of it. Yeah, this requires very, very long, very expensive CNC manufacturing. If you can buy it, you can buy it, but it'll cost around like $300 a bot. Yeah, so it sprays the liquid and starts cutting into it, and then it slowly mills out shapes out of it. But yeah, it is ridiculously strong. If we actually go to an actual 250 combat robot, like a big one, most of the ones are made out of this now, because it is just so unbelievably strong that it's worth it. The other thing that's really nice about billet machining is that if you learn how to do it, if you learn to design with it, you will immediately get hired by somebody. Most likely Lockheed Martin. But because most of our aircraft are built out of billet machined parts, it is, once you get the hang of it and how to design with it, it's a very, very good career path. Yeah. Yeah. Alright. But also, good luck finding a CNC lab that'll let you learn it. Um, yeah, that's money. Alright, so that's all materials. Any last questions before we move on? Okay, so this is wrong. Okay, well, in terms of weapon effectiveness, we need to understand there are two ways to measure the effectiveness of a weapon. The first is just the kinetic energy, and the second is momentum. Right, so this is, if anyone here remembers Physics 1, I know some of y'all are in graduate school, so it may have been a while, but, and some of you guys are we've got one high schooler, so it's very, very, I don't know if you guys have learned it yet, but, oh my god, I'm so sorry for you. RIP Louisiana's education system. But, yeah. Well, yeah, but, yeah. So, these two equations govern how effective your weapon is. Right? Because if you have enough momentum, you could just send robots across the room. Right? Yeah, because just triple momentum. And if you want to, even if you have a lot of, if you have a lot of velocity, you have a lot of kinetic energy. And so you can do a lot of damage. Right? So, notice in both of these equations, momentum and kinetic energy, there are two variables that are the same. What are they? Mass? Who wants to take the other one? It's pretty obvious. Velocity. Right. And so, with momentum, if you make something very heavy and spin up good speed, you can throw things across the room. If you have something that's very, that weighs a bit, but it's also very fast, you can start doing some real damage. So let's look at how that translates into material science. When you talks about breaking a robot, shear stress attack is the first one. The shear stress attack is where you focus solely on the kinetic energy. Because what you're trying to do is you're trying to shear the material. You're trying to, like, take the material and rip it, right? When you're doing that, either by hitting the robot, or when it hits the wall of the field, right? Or when it lands the wrong way, you impart this kinetic energy shock onto it that causes this problem, right? That's shear stress. Impact methodology is purely momentum, right? If you have a robot and you're slamming it into a wall or slamming it into something, right? What you're doing is you're applying a shake to everything inside the electronics. like the electronics, the battery, all of it. You're trying to dislodge as much of the system as possible. And so if you have a screw, that screw's going to come loose if you hit it with enough momentum, right? If you have a wire that's improperly soldered, then that wire is going to rip off if you just shake the box hard enough, right? And for momentum attacks, it's much more than shaking a box hard enough. It's literally like slamming it repeatedly into a wall. And since Battlebots go through that, it's really, really good, right? The last sort of one that John is a big fan of, and that's kind of my fault because I taught him it, was something called penetration theory, right? The really nice thing about both of these methodologies, like the thing that both these methodologies don't count for is to just count for mass and velocity. And so you can take as much mass out of your robot and just build a really heavy weapon that spins really fast. And it'll scare the hell out of people. But if you want, you can also go the other way. We can make a very, very small, very, very thin weapon and just narrow the amount of area you need to cut through the target or punch through it. So if you have a piston that can punch something, right? If you reduce the surface area of it to a reasonable amount, you should just be able to punch through the metal. Or like punch at the metal to where it bends or impacts, right? Instead of applying that force laterally over a wide area. If you also, in the real world, this is basically everything we have to deal with. Because penetration theory is we're being shot at, help us, right? But it's also worth looking at here. It's very difficult to pull off because the smaller the cross-sectional area of your impact, your kinetic equations and momentum equations break down a lot. It doesn't work the same. You would need to look at a fundamental understanding of FEA, which is a mechanical engineering course. Finite element analysis, which is simulations, if you see these two here. But if you have a good understanding of simulating impacting of targets, then you sort of get a good expectation of what is a weak area you can punch through. And so that's penetration theory. Say again, John? No, you don't. It's more fun. It's more fun sometimes. All right. The next we should talk about is looking at this in reverse. It's looking at electronic survivability, right? So, yeah. So all of these, weapon effectiveness, we look at it exactly in reverse. So this is called the brain concept. It actually came from, I learned it from UH. I learned it from Dr. Pepe, which is Dr. Luis Contreras Vidal, who's in charge of the brain lab here at UH, right? Think about whenever you're designing a robot, the electronics are the brain of your robot, right? The wires are the veins, and quite literally, we are exposing our robots to football levels of chronic traumatic encephalopathy, which is brain damage, right? So how do we sit down and say, let's protect our robots from getting hit like this, right? There are three ways. The Malenki is probably the most expensive part of your robot and the most complicated part of your robot, right? Especially if you've never built PCBs before, or even if you have, you know that it's just a very, very difficult thing to work with in terms of repair. And so when we build electronic systems, we make sure we protect it from these three things. Shock and impact protection, which goes back to momentum theory. Bending protection, which happened to us during Turkey Tussle last year. Actually, no, it didn't happen to us, but it happened to someone at Turkey Tussle last year. And then thermal protection, which happened to us at TAMU. So let's look at the maximally invasive lobotomy. Dang. Okay, so the first way to deal with is just shock and impact protection, right? When you have a Malenki inside of a case, tape it down to the floor is just the start, right? If you surround it, if you hot glue to that piece, the hot glue's not going to stay there very long. But if you tape it and then hot glue the edges of it, you have this sort of buffer space, so that the hot glue will sort of get squished, just enough to hold your electronics together, they're also a lot more about where we place our wires, because our wires are also going to come loose. For a lot of the robots I saw when I was working for the club, it was literally just, let's stuff all the electronics in there, let's hot glue it down or tape it down and hope it works. It's not a good idea, because if we put the Malenki on the side of the panel, it's going to get hit. I don't think it's going to survive very long, right? And so we should probably start thinking about where we put our electronics and how do we protect them. Put walls with a little bit of spacing between the wall and the Malenki, so like a 3mm spacing. And when you actually build the robot, fill it with something. Ethan and I experimented with foam. So you put the Malenki in a little foam box, but the foam box in the robot. And so that way the Malenki doesn't shake as much as it needs to. It doesn't bend easily. There's many other methods like using double-sided sticky pads or using other methods. If you just have a little bit of spacing, it'll be fine. Any questions on that? Yeah, I feel like I should have catted some examples from this, but I didn't have time, and so that's that. I don't know how to use it, but yes, I know how to use it in Inventor. I don't use it in 3. Well, the way that I did it before I learned how to use inventors was just draw it, right? Take a screenshot of your wiring diagram and draw it, right? Like draw the path you want the wire to go through, and then go back and say, okay, I want the wires to go down this path. How do I want to do it? Yep. Just start a sketch on where the electronics is going to be. Draw the box. Okay, the Malenki is going to go here. And so I want wires to come out of here, right? Remember, you can drag and drop images. So you can drag a photo of the Malenki into your sketch and say, okay, the Malenki is this size, it's this shape. Let's go here. And that helps out a lot. Makes sense-ish? Any questions on this? All right. I love showing this video just because it's a great way of showing just because TPU will do that. But yeah, okay. The next one is bending protection, right? When your robot's thrown across the room, it's not going to be the same shape sometimes. Even if the same shapeness is a little bit wacky, right? You can, like, even if the bending of it's very, very minuscule, not noticeable, that does a lot to damage electronics. Remember, a resistor on the Malenki at smallest is 1 by 1.5 millimeter. That's tiny, right? And so when it gets thrown across the room and it bends just a little bit, it'll do that. So hard mounting it doesn't really work the same, but mounting it to a very rigid panel, if you can guarantee the panel is going to always be rigid, sure, but nothing is ever always going to be rigid. And so in this robot design I found on the internet, they encased the entire bottom of it in a foam, it's sort of this rubber, like sticky, double-sided sticky tip thing. I know what it's called, just can't remember it right now. When you stick that to it, then when it bends, it doesn't bend the same way. And so you sort of have that sort of shock. Uh-oh. What's going on? Shoot. What? Hang on, something went wrong. Hello? Ah shit, my microphone is... Lie down! 1 minute, guys. Yo. Recording resumed, and we're back. Okay, so from current slide. So just as I sort of mentioned, double protection is a big issue. When you have ESC for the weapon motor, you don't want to stick that next to the Malenki because it'll thermal up, right? Those ESCs get really hot, especially when you don't have good airflow, and so that's a problem. Now, the easy way of solving this for ant weights and for fairy weights is just once the match is over, get it somewhere cold. So like, get a fan and just throw at it, let it cool down a little bit before the next match. But you can also try and do active cooling through some sort of either if your weapon is a spinner, you can sort of spin air into the system, or you can do it some other way. But just don't do what we did, which was take the Malenki and stick it on top of a very, very hot ESC, just a lot of noise, and cause issues. Make sense, guys? Awesome. Alright. Yeah. So the next set of slides here are a little bit confidential. TJ, I'm okay with you looking at it because I don't think it's not going to do any major damage. But I did a lot of this research for my startup that I did, so I'm going to pause this. It's not going to be recorded online. Okay. We're good on that. The last thing we should talk about, and this is going to be a very, very short thing, is process management. And this is kind of a fault of everyone, but let's think about it. Let's look at it, right? The kind of manufacturing we're doing is called just-in-time manufacturing. And this is a real engineering concept. What it is we don't, whatever we need for a robot, we design the robot. And then after we're just done designing the robot, we order all the parts, and as soon as every part arrives, we install it onto the robot. This is called just-in-time manufacturing. The problem with just-in-time manufacturing is that it's very, very, very rigid. Right? We also ends up with a sort of bad expectation that we can build our robots last minute. Yeah. Which I know all of you guys immediately sort of recognized. So, if you want to design something new and creative, you cannot do just-in-time innovation, right? The way you fix that is you do something called selective integration, which is, I know this works. I know this doesn't. I'm going to get all the parts that work now. I'm going to get them in quickly. Get that all working, and then be done. From last competition to this competition, that is what we have changed. So from last competition, literally Oscar and Ethan were like, we've got all the parts today, let's put it all together. Today we're saying, okay, we know the electronics are going to work because we're just going to heat treat them all, put them together, and test them. And they work. And if we're not innovating electronics, that's fine. You cannot rely on just-in-time manufacturing to be innovative and creative. Anyone ever wondered why cars all look the same? Yeah, the reason why is because when Toyota develops the new car, they don't change the process. Because they don't have the ability to control everything from end to end. And so they're waiting on the next part, immediately put it on the car and get it going. So last year's model looks the same as the year before's model, looks the same as the year before's model, with some very minor cosmetic changes. Doesn't create innovation. Think about that. Because as officers, I have shouted at them about that. They are thinking about it now, right? So what we need to do now is we need to say, well, what can we test in pieces before all the parts arrive, right? Let's order some Garolite. Take this Garolite, let's test it against a normal PLA bot. We don't need to test it by putting it into a Battlebot. We can test it by snapping it, breaking into the mechanical engineering labs and testing it, or just throwing it against the wall, right? Come up with a idea for how we want to test it to be stronger, how we want to build the system, like what ideas we want to put into a concept, and go from there. If everyone here who's designed a BattleBot goes back through this slide and says, I like that material, I like this new design process, right? I like this idea for like this truss structure. Don't wait. Get a test part printed. Print just a wall with that part on it. Apply your Garolite and go test it. And then when you know it works, we don't end up blowing our entire budget trying to build all of those at the same time on new untested theories. I'm staring at you, John. John, I'm staring at you. Okay? So when you get out of this mentality of just in time and go into experiment, test, validate, we will really start kicking ass. Alright, that is the end of my slide. I'll wait for 2 minutes for questions. Yeah. Yeah. Yeah, I'll post the PowerPoint to build robot tutorials, which I've been posting a lot recently. Yeah. Yeah, so it'll be right here. Yeah. Did I give you guys a lot to think about? Alright. And so, yeah, so genuinely start thinking about these ideas, start thinking about these concepts. If you get any of them working, go for it. Some of them I know work, some of them I don't, but there's no way to know that without doing a small scale test and then saying, okay, small scale test works, let's go to big scale, right? Okay. Anyone have any last minute questions before I sign off? Now's your chance. Okay. I will be there on the 21st to celebrate the end of Battlebots party and the second general meeting. The poll that I've put out on Discord, sorry Caitlin, I know you're gonna do it, but I did it already. Was tacos one. So I'm thinking either getting a Chipotle catering or Taco Cabana catering. That should be good enough. Yeah, that probably would have been smart. I should have waited for that, huh? Just shoot it. Justin's a little iffy on it. Just shoot it. But yeah, we all good on that. All right. See you guys on the 21st.